Algorithmic topology, or computational topology, is a subfield of topology with an overlap with areas of computer science, in particular computational geometry and computational complexity theory. A primary concern of algorithmic topology, as its name suggests, is to develop efficient algorithms for solving topological problems using topological methods from computable topology to solve algorithmic problems from other fields. Major algorithms by subject area. Algorithmic three-manifold theory. A large family of algorithms concerning three manifolds revolve around normal surface theory, which is a phrase that encompasses several techniques to turn problems in three-manifold theory into integer linear programming problems. Rubinstein and Thompson's three-sphere recognition algorithm. This is an algorithm that takes as input a triangulated three-manifold and determines whether or not the manifold is homeomorphic to the three-sphere. It has exponential runtime in the number of tetrahedral simplexes in the initial three-manifold, and also an exponential memory profile. Moreover, it is implemented in the software package Regina. Saul Schleimer went on to show the problem lies in the complexity class NP. The connect-sum decomposition of three manifolds is also implemented in Regina, has exponential runtime and is based on a similar algorithm to the three-sphere recognition algorithm, determining that the Seifert-Weber three-manifold contains no incompressible surface has been algorithmically implemented by Burton, Rubinstein and Tillman and based on normal surface theory. The Manning algorithm is an algorithm to find hyperbolic structures on three manifolds whose fundamental group have a solution to the word problem. At present, the JSJ decomposition has not been implemented algorithmically in computer software. Neither has the compression body decomposition. There are some very popular and successful heuristics, such as Snapier, which has much success computing approximate hyperbolic structures on triangulated three manifolds. It is known that the full classification of three manifolds can be done algorithmically. Conversion algorithms. Snapier implements an algorithm to convert a planar knot or link diagram into a cusp triangulation. This algorithm has a roughly linear runtime in the number of crossings in the diagram, and low memory profile. The algorithm is similar to the Werthinger algorithm for constructing presentations of the fundamental group of link complements given by planar diagrams. Similarly, Snapier can convert surgery presentations of three manifolds into triangulations of the presented three manifold. D. Thurston and F. Costantino have a procedure to construct a triangulated four-manifold from a triangulated three-manifold. Similarly, it can be used to construct surgery presentations of triangulated three-manifolds. Although the procedure is not explicitly written as an algorithm in principle, it should have polynomial runtime in the number of tetrahedra of the given three-manifold triangulation. S. Schleimer has an algorithm which produces a triangulated three-manifold, given input a word for the mapping class group of a surface. The three-manifold is the one that uses the word as the attaching map for a Heegaard splitting of the three-manifold. The algorithm is based on the concept of a layered triangulation. Algorithmic knot theory. Determining whether or not a knot is trivial is known to be in the complexity class NP. The problem of determining the genus of a knot is known to have complexity class PSPACE. There are polynomial time algorithms for the computation of the Alexander polynomial of a knot. Computational homotopy. Computational methods for homotopy groups of spheres. Computational methods for solving systems of polynomial equations. Brown has an algorithm to compute the homotopy groups of spaces that are finite Postnikov complexes, although it is not widely considered implementable. Computational homology. Computation of homology groups of cell complexes reduces to bringing the boundary matrices into Smith normal form. Although this is a completely solved problem algorithmically, there are various technical obstacles to efficient computation for large complexes. There are two central obstacles. Firstly, The basic Smith form algorithm has cubic complexity in the size of the matrix involved, since it uses row and column operations, which makes it unsuitable for large cell complexes. Secondly, the intermediate matrices which result from the application of the Smith form algorithm get filled in even if one starts and ends with sparse matrices. Efficient and probabilistic Smith normal form algorithms, as found in the Linbox library. Simple homotopic reductions for pre-processing homology computations, as in the Perseus software package. Algorithms to compute persistent homology of filtered complexes. Books: Thomas Kaczynski, Konstantin Moskaikov, Marian Morozek. Computational Homology. Springer. ISBN 0-387-40853-3. Afra J. Zomarodian. Topology for Computing. Cambridge. ISBN 0-521-83666-2. Computational Topology. An Introduction. Herbert Edelsbrunner, John L. Hera, AMS Bookstore, 2010, ISBN 978-0-8218-4925-5.